Hello, esteemed judges. My name is Taiji Zhang, together with my team members, Associate Professor Dr. Haja Alias, Dr. Amnani Shamjuddin, and also Dr. Muhammad Sukri Muhammad Yusuf. I'm incredibly proud to present our research in Young Engineers Awards for Innovation and Sustainability. The title of our project is Metal Organic Framework-Based Heterostructure Catalyst in Smart Photothermal System for Carbon Dioxide Conversion to Fuels. And it is an honor to share our work with you today.
Our world is facing an escalating crisis of global carbon dioxide emissions, which demand urgent, actionable solutions for carbon capture and utilizations to combat the climate change. Currently, there is a surging demand for renewable fuels because of the war, right? And yet, we are lack of sufficient eco-friendly and energy-efficient technologies that are compatible with existing infrastructure. Furthermore, as we look towards the future, there is a pressing need to comply with the low carbon aspirations 2040, as you can see here, and also tap into the power to gas market by 2020 up to $40 billion. Core of our project is to reduce these carbon dioxide emissions and efficiently converting captured carbon into valuable renewable energy carriers like CH4, methane, and CO, carbon monoxide. We achieve this in a cost-effective and sustainable manner by developing a smart photothermal systems. So to deliver this, we synthesize a MOF-based heterostructure catalyst consisting of three components. First is copper MOF, metal organic framework, and copper nickel lanthanum layer double hydroxides, and also graphitic carbon nitride. So we integrate these components using a simple mechanical assembly approach, and the resulting catalyst is then loaded into the fixed bed reactor, as you can see inside the image. And by applying simultaneous light irradiation and also external heating, we drive the carbon dioxide hydrogenation process, achieving enhanced conversions while deliberate minimizing energy inputs. The results has been remarkable. So by harmonizing the solar and thermal energy at low optimal temperature of 250 degrees Celsius, as shown in the bar chart here, right? So we suppress the catalyst sintering and caulking. So we want to prevent the caulk formation because it will reduce the catalyst efficiency. And also we delivered 2.1 volts of boost in our fuel production as compared with the just thermal energy supply. Alright, so under visible lights, alright, the photothermal conditions, our product rates rose significantly up to 16.9 millimoles per hour methane. And furthermore, our mechanical assembly heterostructure outperformed the non-optimized counterparts. And also, as you can see inside the figure here, we have using the characterization of PSAM, and we capture how the catalyst looks like. As you can see, it is very fine dispersions and is prior to giving more active sites for the carbon dioxide to adsorb on the catalyst surface and increase the catalyst efficiency.
So this solution is directly aligned with the ICAME priority topic area of environmental protection and improvements. So by achieving an efficient, low temperature fuel production systems, the systems that close the carbon loop, our work fundamentally support the global sustainability targets. We are tackling the climate mitigation heads-on while advancing the technological frontier for a clean, accessible energy. Right? So goes to the benefits towards societies. So these technologies scale beautifully over time. So in short terms, the society benefits from a system that slash the energy use traditional requires for carbon dioxide conversions that for traditionally maybe it will use up to 500 degrees Celsius in supplying the thermal energy for the reaction to occur. However, our smart photothermal system, it just requires 250 degrees Celsius with the light only. And then in the medium terms, we aim to accelerate the commercializations of this low energy technology, and our next steps is involved in scaling up the mechanical assembly to continuous flow synthesis and conducting 1000 hour stability trials and testing the system under the real sunlight with concentrator. So when we apply the real sunlight, we can save costs of 12 hours using the solar simulator. Yeah, there's further reduce our costs. And then this directly positions us up to supply clean fuels to the 40 billion power to gas markets, right? So finally, in long terms, this technology provides a sustainable pathway to energy security without fossil fuels dependence, and it helps to meet the 2040 low carbon aspiration goals, reduce the global emissions, and also drive the job creation within the renewable energy sector. With that, we believe that the smart photothermal system are the key to turning our carbon liability into a renewable asset. So thank you to the judges for your time, and thank you to the Ministry of Higher Education Malaysia for supporting this vision.